Hello everybody, ta ta ta. Welcome to the Funtastic Academy with me, Ayush Prasad. Hello everyone, welcome back to the Funtastic Academy. Today we are going to dive into the wide world of logic gates. Last episode we learned about how your computer does math. But doing one addition or one subtraction is not useful if your computer can't chain them together in logic. So that's what we're going to learn about today. Logic gates and how your computer thinks. Now, before we get to logic gates, we need to answer last episode's quiz question. What German mathematician who also invented calculus first made the binary system as we know today? The answer is Leibniz. Leibniz was a German mathematician who is sometimes called the inventor of calculus. Newton invented it many years before him, but since Newton did not publish his findings, Leibniz is sometimes credited with it and sometimes not. But doubtless, he invented the modern notation that we use for both calculus and computing. So, now let's dive into the wide world of logic gates. Dive in! In your computer, there are 6 types of logic gates. But what are gates? They are tiny chips which take inputs, do logic, and give outputs. Logic gates all have symbols and they are all displayed right here. The AND gate, the NOT gate, the OR gate, the XOR gate, the NAND gate, and the NOR gate. These are all the important gates used in computing. And they all serve a simple function. For example, the AND gate takes 2 inputs. These inputs can either be 0, meaning false, or 1, meaning true. The AND gate simply outputs the first input and the second input. For example, if both the inputs coming into it are true, it will output true, because a true and a true is a true. But if one input is true and one input is false, they will output false, because if one thing is true and one thing is false, then both of them combined are false. So, the AND gate only outputs true when both of the inputs are true. The NOT gate simply reverses whatever its input is. If it's given a true, it outputs a false. If it's given a false, it outputs a true. And the OR gate outputs the first input or the second input. If either of the inputs are high, they are true, the output is true. The OR gate is only false when both of its inputs are false. In that way, it's kind of a reverse to the AND gate. We'll see what this means later. Now, these gates, XOR, NAND, and NOR, can also be thought of using mathematics like this. But a much simpler way of thinking about them is by using the truth table. Truth tables are tables of mathematical machinery that can be used to efficiently analyze what logic gates do. They were first popularized by the logician Ludwig Wittgenstein in his book Tractatus Logico Philosophus. Now, truth tables can be used for simple calculations. For example, the NOT gate, which is just reversing. If the input is 0, it outputs a 1. If the input is 1, it outputs a 0. The true power in truth tables, though, lies in their ability to express all combinations of inputs. Let me explain. Here we have all possible combinations of 2 inputs. They can both be false, one of them can be true and the other could be false, or both of them could be true. 4 possibilities. And the AND gate only outputs a true if both them are true. Otherwise, it outputs a false. So, in this simple 3 by 4 table, we've captured the essence of an AND gate. And we can do the same thing for all the other gates. Here are 2 other important gates. The OR gate. Again, we can see all combinations. This time though, the OR outputs only false when both the inputs are false and outputs true otherwise. Finally, the XOR gate. There are many ways to think about the XOR gate. But the way I find easiest is simply in terms of equality. If 2 inputs are the same, it outputs false. If 2 inputs are different, it outputs true. And that's quite a hard thing to make using circuitry. We'll see that later. But it's really simple to encode that in this table. If both inputs are false, it outputs false. And if all 2 inputs are true, it also outputs false because in both cases the inputs are the same. But if the inputs are different, it outputs a true. That's AND, NOT, OR and XOR all done. What about NAND and NOR? They're simply what you get if you take a NOT gate after one of the gates we've already discussed. For example, the NAND gate gives a true if not both the inputs are true, but it only gives false if both the inputs are true. The NAND gate is a very important gate, and we'll see that next episode. Now, the NOR gate does the same thing for the OR gate. If in the OR gate both inputs are false, it outputs a true. But if just one or both of the inputs are true, it outputs a false. So these 6 logic gates might sound simple, but they can be used to do all of computing. But I'll talk more about those in the next episode. So, I hope you enjoyed that video. We learned about logic gates and how they can simply be expressed using truth tables. But one question, who invented truth tables? Wittgenstein surely popularized them, but who first thought about them? Well, that's today's quiz question. Send me the answer and I'll see you next episode of the